Here is simulation and implementation diagram of rectifier with a finite impulse filter which has uniform coefficients. First we have sigma delta modulator, analog signal that has to be rectified. Then we have delta sigma demodulator, which is nothing more than finite impulse response filter of length of 100 bits. Down there we have our encoder, rectifying encoder with belonging finite impulse response filter, which is identical to the upper one. We did theoretical analysis and simulation as well, and we have shown that output of our rectifier is equal 2 times absolute value of demodulated signal or 2 times absolute value of input signal. Experimental results of Dr. Wei show this situation as well. And now he will demonstrate you how it works and why it works.
So we have implemented the whole diagram with the hardware. Here we have 2 sigma delta modulators, and we are using one of them. And this sigma delta modulator is this part. So every digital circuit, including the delay and the summing and the XOR circuits, they are all in this FPGA. And the output of the FPGA is a 8-bit digital signal, which is fed into this digital to analog converter, and it is converted back to the analog signal. Now the FPGA is controlled by this computer. It's programmed with Verilog hardware description language. Okay, let's press the red button. Alright, let's start the demonstration. So the whole setup is hooked up with one signal generator and one oscilloscope. In the signal generator, we have 2 channels. The first channel is the analog input. It is 11 Hz, 550 millivolts sine wave. The second channel is the digital signal for the clock of the sigma delta modulator. It is a 200 kilohertz sampling rate, 3.3 volts amplitude. So the first thing I want to demo is when I changing the sampling clock of the sigma delta modulator, you're gonna see a finer waveform or larger step waveform. So if I increase the sigma delta sampling clock, you're gonna see it is getting finer. Or if I decrease it,
Go with amplitude a little bit down. Yeah. Mm-hmm.
Okay, so let's go with the amplitude a little bit down. Okay, yeah, now this is very clear. So now we can see more and more steps because the output is coming from a DAC. So now I move it back to our standard 200 kilohertz. Okay, the second thing, I can change the input frequency, so the output follows. And now I'm gonna change the amplitude. So the amplitude is getting smaller and smaller.
That's fine.
Yeah, so move it back. So the most interesting part is that we can demonstrate the offset. So theoretically, waveform rectified with offset, you're gonna see uneven sine waves. Let me see what's the offset. Okay, now let's start with offset. Oh, it's too much. Keep it increasing. So you can see some part is getting larger and some parts is getting smaller, until we can see the whole sine waveform. Oh, the peak is saturated. So that is everything for our demonstration. It shows the first sigma delta low complexity rectifier in the world and with the real implementation. Thank you.